shall I start?
Are you ready with your presentation?
Yes.
You should have emailed me the present. You can email me now or after the class. It's fine. Well, you can start. You can start whenever you are ready.
Oh,
You know how to connect to the HDMI.
yes, I've already connected it.
But we don't see your screen. Yeah, now we see.
Hello. Can everyone hear me?
Yeah, we can hear you.
Okay. So hello everyone. So today I'll be giving like a short presentation on some of the some useful topics for your project. Essentially, I will be walking through some examples of how to code FFT in Verilog, as well as some of the things which you need to keep in mind when you're making these designs. So as you've seen in the class, the FFT is a fast and optimized way to implement the discrete Fourier transform, and it's an efficient algorithm which needs only n log n computations versus n square for the DFT when n is a power of 2. So the FFT hardware consists of 3 main building blocks. So the first is the butterfly unit, the second is the rotator, and the third is the delay switch delay. So I'll be going over each of these units in details, and if you have any questions, feel free to stop and ask them. So essentially the butterfly unit, as you've seen in class, it performs 2 operations. If it's given 2 inputs, the first output is the summation of both those inputs, and the second output is the difference of both those outputs. And that is what this diagram here represents. The only thing which we need to consider is when we are building the hardware is that these will be complex numbers, depending on what's your project type. If it's a real FFT or a complex FFT, if the data path which you're working on is complex, that would mean that you would have a separate real and imaginary parts. So in terms of hardware, what that would mean is that you would essentially replicate the same function for both the real and imaginary parts. So you'll have like y1 and y2 real and y1 and y2 imaginary, same way we had y1 and y2 earlier. And how we would actually implement these in Verilog, we can either implement them. These will be directly adders, like how you have used in the projects, so in the homeworks thus far, or we can implement it as a subtractor. If you just in Verilog, if you just directly implement it as a minus b, or as we've seen in the earlier homeworks, we can also implement a subtraction as inverse of the second number and an addition of 1. So the second block which we're going to talk about is the rotator. So this is essentially the block that multiplies the result which you get with the twiddle factor. So we have seen that whenever we have an FFT, we have a twiddle factor which is of the form of w to the power k of kn, where k is the number which you see on each of the branches and n is the total endpoints of the FFT. And that essentially becomes e to the power minus j2 pi k over n. So we do not directly implement an exponential function in any of the hardware. What we do is that we use Euler's identity to replace this exponent as a cosine and a sine function. So this e to the power minus j 2 pi k over n will become cosine of 2 pi k over n minus j sine of 2 pi k over n. The other thing which I would like to point out is that since the values of k are, the range of k is fixed beforehand, we again would not implement a sine or cosine function within the hardware. What we would rather do is that we would store pre-computed values for cosine and sine values for all the values which we need. So for example, if k has a range of 0 to 3, we would essentially have a lookup table of size 8 which would store the cosine values for k 0 to 3 and the sine values of k 0 to 3. I hope that's clear. So that's about the twiddle factors themselves. The second part is we need to do a complex multiplication. So that means we have a real and imaginary parts. So if you just take a standard form of a complex number as, let's say, a plus jb, and the second number c plus jd, so we will end up with a formula which looks like this. So this is essentially 2 additions and 4 multiplications, the first line here. So the reasons only 2 additions is because we treat, again, we always, when we're working in complex domain, we always treat the real and imaginary parts separate. So then this would be, so this is the real component. So this would be 2 multiplications and 1 addition. Similarly, this is the imaginary component, that would be 2 multiplications and 1 addition. And the below circuit here shows what that would look like if you were to design it in hardware. If you want to reduce the multipliers, there's an alternative implementation which you could try out, which has just 3 multiplies, but it compensates it with having 5 additions. Yeah, and the other thing which I just wanted to point out is that certain k's have trivial multiplications. So what does that mean? So for example, if you have k values like 0, n over 4, n over 2, the value for this entire equation comes to 1, minus j, minus 1, j, and 1. So essentially when you have these kind of operations, it's why do we call it trivial? So multiplication of 1 is trivial, but even a multiplication of minus j, all that implies is that you interchange the real and imaginary components while changing while appropriately handling the sign, right? And similar with a j operation. So whenever we see these kind of multiplications within the like the DFG of the FFT, just know that these are not real multiplications, but they're often trivial multiplications. So the next block which I'll talk about is the I put switch delay switch, but it's the delay switch delay. So essentially, what this block does is it interleaves two blocks of data from 2 channels into one another. So for example, let's say you have channel 1 which has x, channel 2 which has y. So and there's an ND here. So what it will essentially do is it will line up the value of x1 with the value of x of n plus 1, and similarly the value of y1 with the value of yn plus 1. So the main thing which you need to know for this kind of a circuit is that when we are getting the value 0 from, let's say, a control signal, a value of 0 means that we want to essentially keep the order for the first path as it is, and we want to delay the second path. A value for 1 means we want to bring the values which are further behind on the first path to the front. So that means, so in this particular example, if we wanted to line up x1 with xn plus 1, the first n values would be 0. So then the first n values of x would be stored within this register, these sets of registers here, and then at t is equal to n plus 1, which would be when this input is here, then we would set the value to 1, and then this the input would come directly on this path here. And then at the same time, the first value would be coming out of this set of registers here. So that way these two are lined up. So one important thing to note when you're doing this kind of system is that you can see that in our initials setup that this was starting at t is equal to 1, but the very first values of use actually come at t is equal to n plus 1 here. So this system is internally has a latency of n, even though it has 2n delays over here. And the other thing which you should note is that even though the system has a latency of n, in reality, when you think of it in terms of timing or critical path, this does not actually break up your critical path, because you can see there is actually a path which goes from the input to the output with no delays at all. So from a design point of view, from a critical path point of view, if you're trying to meet some sort of timing, you should know that even though this adds a latency to the system, this still does not break up any of your critical paths. So these are the three basic building blocks which you will use to build up FFT modules. So maybe I'll take a quick pause here for any questions.
So to break the critical path, they have to have a pipelining cut set.
Yes, right. So yeah, even though there are registers present here, it does not break the critical path. So if you need to actually break the critical path, you need to insert your own manual pipelining cut sets. Okay, so if there are no questions, I'll go to the next part, which talks about fixed point arithmetic. So I seem to have a repeat slide, yeah. So essentially, fixed point arithmetic, which we have seen before in the homeworks, represents any sort of number as an integer portion and a fractional portion. So in this case, if we have like a qx.y format, that would mean there are x bits in the integer component and y bits in the fractional component. And as we've seen earlier, so that would basically translate to this sort of an equation when we want to like convert from this binary number to the real number. So for example, if you see this 4.625, so you can essentially create it like the integer portion 4 is 0, 1, 0, 0, and the fractional portion is 625, which is essentially 0.5 plus 0.125, or rather 2 to the power minus 1 plus 2 to the power minus 3. So this is the main format which we will use for these projects to represent numbers, which is the fixed point format. There is the floating point format as well, which is like the standard IEEE floating point, but that often involves special hardware. So but for the purposes of this project, usually we stick to the fixed point format itself. So there are certain things to note when you actually use these fixed point formats. The first thing is that the tool would just directly consider these as signed or unsigned integers. The tool has no idea of what representation you actually interpret this as, right? From the tool's point of view, it's just a set of 8 bits. So it's always up to the user or the designer to actually you interpret whatever results you give in and what results you get out in the right formats which you need. Okay? And for the project, what we generally do is that we try to keep a fixed format for the entire length of the project. So as in a fixed width. So what that means is that if at this input of stage 1 you have 16 bits, the output of stage 1 will also be 16 bits. It need not be the exact same format, which we will go through in the next slide, but the number of bits in each stage will remain constant. Any questions so far? Okay, so what do I mean by the format may not stay constant? So when we are working with fixed point numbers and adders and multipliers, generally we'll have something which is called truncation or scaling. Essentially, when you think about it, right, when you add two n-bit numbers, the result is actually going to be n plus 1 bits, right? But from our point of view, if we want to keep the width fixed, what that means is that when we are designing, let's say, any sort of circuit, let's say we start with two Q1 plus 7s, so the actual result would be a Q2 2.7, right? But since we're interested in the most significant bits, we would truncate that result to a Q2.6. So we would reduce so we would basically truncate the LSB. But what that also means is that now the range of our inputs has changed. So if we initially started it in a range from -1 to +1, after we have gone through any single adder, because of the result we had to truncate the least significant bit, our range is now like -2 to +2. So does that make sense to everyone? So the second thing is rotators, where essentially we're doing a multiplication. So when we are doing a multiplication, again we know that all of our, let's say we start off in the Q1, let's say 1.7 range, we know all of our values will be 1 or less, right? So that way, even when we multiply the values, we know that the result should be between -1 and 1. So we can actually use that fact, like exploit that fact to actually design like how do we truncate or scale the next stage. So for example, if we are multiplying two q x dot y numbers, the result would actually be a q 2x dot 2y number. But since we know that the range is still limited to +1 to -1, what we would do is we would essentially truncate it in such a way that we would maintain the Q1.7 format for in like what I was explaining earlier. So essentially you would truncate the MSB X bits and the LSB Y bits. So this only works if we started off with the assumption that everything is between the +1 and -1 range. If we worked, for example, with integers, this would not hold good anymore. But the caveat to this kind of an operation is that if you remember the design of a rotator, it has an implicit add within it. So from what we discussed earlier, because of that add, we would ideally need to perform a scaling or basically scaling and truncation for this add operation here, right? So that brings us to the question is like how do we handle this bit growth? So bit growth essentially is saying that at each stage every adder needs to have a +1 bit growth, and a multiplier essentially doubles the number of bits at each stage. So the first simplest method which you can think of to handle bit growth is at every single adder you have a 1-bit truncation and like a 1-bit scaling. So that means that the adder blocks of your butterfly has a 1-bit truncation. Each complex multiplier also has a 1-bit truncation because it has an adder within it. And therefore, essentially you have 2 bits of truncation per stage. So now if you have something like a 1020-point FFT, that has 10 stages, and in those 10 stages you have 10 adders and 9 multipliers. So what that essentially means is that by the time from start to finish, you would have a total truncation of 19 bits, which is a lot. That means if you want to have any sort of a signal with a good enough like signal to noise ratio, let's say if you want the signal to noise ratio to be at least 8 bits, then you need to start off with a signal which is at least 19 plus 8 bits or like 27 bits. The second option is to actually perform bit growth itself in the different stages. That means after stage 1, you would have, let's say, n, if we started with n bits, after stage 1 you would have n plus 1 bits, after stage 2 you'll have n plus 2 bits and so on. But the other problem is that this could, if you have a lot of stages, that means you could start off with a small signal, but you could end up with a very large signal. If you start with 8 bits, you will finally end up with something like 18 bits in your output after, let's say, 10 stages. But this is at least has some better alternatives than the first approach, because there you would actually need to have a very high precision from the start, and here you can maybe do it selectively on some stages. The last approach, which is probably a simpler approach and maybe it's like a compromise, would be that to actually consider a 2-bit reduction or truncation at each stage is an overkill. So what do I mean by that? So if you have an FFT where all the inputs are limited to +1 and -1, the result of the FFT, the largest value that you can get in terms of absolute value would be, let's say in this case n plus or jn, right, in the real parts or the imaginary parts. So if you really need to only support eventual growth to the value n, so in reality you only need, the circuit only needs to grow by log n plus 1 bits, right, because n cannot be represented in log n bits, it needs log n plus 1 bits to represent n. So this is usually a good compromise between the two. So now instead of actually growing it at 2 bits per stage, what you would do is you just grow it at 1 bit per stage. So the number of stages is log n, and you, in the first stage you would essentially grow it by 2 bits, or rather you truncate it by 2 bits. So the first stage you basically scale and truncate by 2, and all subsequent stages are truncated by 1, and that way you can actually ensure that your result will fit within the the final result will still fit within the accuracy which you require. So is everyone clear on fixed point arithmetic, truncation and scaling? So these are some of the main issues which you'll face when you're actually designing the data path for the entire FFT. Okay, if there are no questions, I'll go to the next slide. So for the next slide, what I'll do is I will walk you through like an 8-point radix 2 DIF FFT example. So this is the R2 MDC example. So I'll show you how we would implement the butterflies, how we would implement the rotators, and how would you implement the delay switch delay block. So I'll only show it for the first stage, but from what we designed in the first stage, you can extrapolate it for stage 2 and stage 3 based on the diagram here. So first, let's look at the butterfly example. So this is a simple code which directly implements the butterflies as the definition is. Like how I described it, as we have a real path and an imaginary path, we'll essentially do, let's say, real 1 would be like the sum of the 2 real inputs. Real 2 would be the subtraction of the 2 real inputs, and similarly about the imaginary 1 and imaginary 2. Right? So you can essentially see, if you remember the diagram, we had 4 adders. This is literally the implementation of those 4 adders here. So now, like we discussed earlier, because we are working in fixed points and each adder would need a bit growth and truncation. So this is what this is essentially showing. So when you're adding 2, let's say, data width numbers, your final result will be a data width plus 1. But then since we want to keep a fixed precision for all the stages, you can see in these set of lines here, what we're doing is we're keeping the MSB like D bits here. So we are essentially, by using this code, we are ignoring the LSB of the result. So that way we have both truncated the 1 bit as well as we have scaled it up. So now if your initial values of the range of +1, -1, now at the end of the stage, your values will be a range of +2 to -2. And similarly, in the next stage, it would be +4 to -4, and the stage after that would be +8 to -8, and so on. So the second example is the rotator. So essentially, this is how we are implementing the complex multiplication within a hardware block. So the first block which you actually see here is implementing what I described earlier, is that we just pre-compute the values of the sine and cosine lookup tables, and we just store it in files which we just load here. I'll show you an example of what this file looks like in like a couple of slides from now. But essentially, we pre-compute all the values and store it in the required fixed point format over here. And the multiplier, so I've just shown the first case here where we have 4 multiplies and 2 adds. So if you remember the figure which we had here. So essentially, we have these 4 multipliers, these 2 adders to create the real and imaginary components. So this code is a direct implementation of that. You can see the 4 multipliers here, and you can see the 2 adders here. So this is the first adder, and this is the second line is the second adder here. So here in this code, you can also see how we are handling the bit growth and truncation. So here, essentially, when we are multiplying these 2 numbers here, which is of size which is of width, data width, and of coefficient width, your final result would be like data width plus coefficient width in terms of size. And then when we actually come to the adder, so you can actually see that in the code here, I've actually done that truncation here. So for the first result, I've done like data width plus coefficient -2 down to coefficient width -1. So this is essentially taking like the set of results which you're interested in, right? Remember, if we started off with, let's say, a 1.7 format, the result would be a 2.7 format. So I'm extracting the middle 1.7 out of that format. So that's exactly what this code here is doing. It's extracting that portion of the format out. Similarly, for the second data part, so the second multiplication also, we're extracting that portion. We add the 2 results together, or in this particular case, it's a subtraction. And then we are just ensuring that the result is data width, because we have already handled all the truncation and scaling for this thing. We do not want it to grow anymore, so we just keep the result to a data width. So is this part clear to everyone, how we are implementing a complex multiplier in Verilog? So here is essentially an example of what those blocks look like for the LUT. So if you remember, we had over here this sine ROT and the cos ROT. So this is a sample LUT for a different architecture. This is not directly for the R2 MDC, but you would create something similar. So essentially what you do is, so this is for a 16-point implementation. So you would essentially create, so this is a 16-bit, and I'm not sure exactly how many points this is, but you would essentially store each pre-computed value for all of these signals here. So for example, here this would be the value 0, and then here, which is line 5, which I'm not sure is very readable, but where my pointer is, that is the value 1. So you can kind of see that this signal is oscillating from 0 to 1 and so on. And then here this is all ones is essentially 0, and then it goes to a -1 here.
But you can't represent 1, it will be 1 minus delta.
Yes, so that's exactly the thing here. So if you see here, it is like 0 and all ones here. So that is that 1 minus delta. But in
you are doing the bypass, when multiplying by 1, you actually don't multiply by this. Bypass.
Yes. So that
Bypass.
Yes, so that is what I was talking about, those trivial multiplications. So if you're multiplying by +1, -j, -1 or plus j, you normally don't actually pass it to the rotator, you just use bypass circuits or like interchange circuits to handle those kind of situations. So yeah, this is essentially what these lookup tables look like. And in terms of format, so all this include block in Verilog does you can think of it as text replacement. So if you were to replace the text of that file directly in this file, how would it need to look like? That's essentially the format you need to store that file in. Does that make sense? Okay, and the next example is the delay switch delay block. So here I've essentially shown the switch part of it because you've seen how to implement delays before with flip-flop. So here is how you implement the switch. And just like before, we essentially treat the real and imaginary parts of these signals separately. So essentially, you would have a data 1 real, data 2 real, data 1 imaginary, data 2 imaginary. So yeah, that's the only differences you consider when you're working with real versus imaginary, is that you just treat each of those data parts separately. So yeah, and like discussed before, a D delay switch delay block basically aligns data which is D cycles apart. And usually for these kind of circuits, we derive these controls from counters. And I'll show you an example of that in the coming slides. So here is an example of, like, we're just going to walk through the first stage of how the data actually moves through the R2MDC structure. So essentially, if you consider that at T0 we are getting the value x0 and at T7 we are getting the value x7. So essentially this is an 8-point FFT. So in the first 8 cycles we get all the data we need. So the top branch has a delay of 4 and the bottom branch has the value passed on directly. So if we actually see after a delay of 4 or as t is equal to 4, the top branch would still have the value x0, whereas the bottom branch would have moved till x4. And for this particular circuit, we are not interested in the values which are there in these time points. So that's why I've just left it out as a dash. So as you know that we actually have a 50% utilization when it comes to R2MDC. So that's what these dashes actually represent here. So now after we perform the butterfly operation, essentially we would then need to perform this complex multiplication. So if you remember the DFG for the 8-point FFT, you would essentially you would multiply the value which would come on the path x4 with the value of W0, the value which would come on path along with x5 with W1, x6 with W2 and x7 with W3. Not the direct inputs, but the result of the butterfly in that same path. Does it make sense? So similar to how you need to keep track of how the data is flowing, you also need to keep track of which cycles it's arriving at, so that you can design the multiplier to read the appropriate inputs at the right time. So this is one form of control which you need to implement. How do you ensure that the twiddle factors are being multiplied in the right cycles? So for example, things which you need to consider is that if you had a delay after the butterfly unit but before the rotator, essentially you would need to ensure that the twiddle factors arrive 1 cycle later. Right? So instead of this being t equal to 4, this would be t equal to 5 if, let's say, you had a pipeline stage here. Generally speaking, when you have control signals, you don't just directly pipeline the control, but you just change the control. So what that means is that one way you could do it is you could think of that like this twiddle is just coming from another block here, and then you put a pipeline on that path as well, right? But then you'd just be unnecessarily creating registers when not needed. You can just, instead of just the easiest solution would be instead of reading the 0th value, just read the first values, for example. So yeah, generally in control, we avoid actually explicitly designing the pipeline register, but we just move the values as for what we need. So that is after the first butterfly and the rotator. So then after that value, so again at t is equal to 4, we would have x0 path, the value which would be on x0 here, and the value which would have been coinciding with x4 on this path at the input of these registers. So now at the second stage, what is our essential goal? Our essential goal is to align the x0 and x2. So essentially align data which are 2 apart in this case. So we want to align x0 and x2, we want to align x4, x6, x1, x3 and so on like that. So how would that be in terms of implementation? So have a look at like the first example. So in the first 2 cycles we would have the value 0. So that means this, let's say this value x0 and x1 enter these 2 registers here. Then in the next 2 cycles, and similarly x4 and x5 is entering this register here. In the next 2 cycles, we actually have the value 1 here. So what that means is that whatever is on this path will appear on this path, will come from the top path, will come to the bottom path. Whatever is in the bottom path will come to the top path. That means this will be at time step number 6, which essentially corresponds to x2, would now come on the bottom path. And whatever is at this point here, which would be x4 since we have 2 delays here. So at time 6, this would still be x4 because we have the 2 delays. That would come to the top path. So now if you see the output at this stage at time t is equal to 6, you would have x0, x2, x1, x3. And then by the time this the x4 and x5 pass through these registers, that would be time 8 and time 9. So is it clear like how we can actually use the delay switch delay to actually align the data to what we need? So now the question is, how do we actually implement this control? So as you can see that this is a pretty simple control circuit. So you just have a repeating patterns of zeros and ones, right? So if you think of it, if you implement a 2-bit counter, so that would just be taking the most like the first bit of the 2-bit counter. So example here I've shown a 3-bit counter. So if you take the first bit, you have the same pattern which you need 0 0 1 1 0 0 1 1. Right? So that seems simple enough. The only thing which you need to be careful of is once you actually implement pipelines in your circuit to meet timing, you would need to appropriately move these control signals. So for example, if in this case you needed 2 pipeline registers, let's say one after the butterfly and one after the rotator. So essentially this control circuit should also move by 2 cycles to make sure that it matches the data once it reaches this point here. Does that make sense?
So what does that mean? That means you take that control. I can see some of that could be from the counter itself.
Yes.
But some cannot.
Yes.
And then you place additional delays.
Yes.
To the control bit.
So generally, it depends on what are we doing. So in this simple case, since it's cyclic with 2 and we are shifting by 2, that would just mean like inverting the signal.
Mm-hmm.
But let's say if you're shifting by 1, what you could either implement a delay to shift that bit, or you could essentially have a condition which would be set high when like certain values are ahead, like a normal switch. Let's say if the values are 1, or if the value is equal to 1 or 2, then set the value high, otherwise set the value low. Okay.
How many lookup tables are there for all the twiddle factors?
So it depends on which type of FFT we are implementing. Like let's say if we are implementing like a standard radix 2, generally we need up to n over 2 twiddle factors.
Yeah.
So basically, if it's 8, we would need up to W3. But in reality, if you're more constrained, you could basically represent in half of that, because you can represent sine in terms of cosine.
Yeah, I wasn't asking that. So there are two multipliers here, right?
Yes.
So are both multipliers reading from the same lookup table, or there are two separate lookup tables for these two multipliers?
The easier implementation would be two separate lookup tables, because if you think of how it would be implemented in hardware, this would be essentially implemented as a ROM.
Yeah.
So it depends if you implement it as a single port ROM versus a dual port ROM. So a single port ROM means it can only read one value at a time. A dual port ROM means it can read two values at a time.
Okay.
So, but generally, yeah, the number of lookup tables would be the number of multipliers divided by the number of ports each ROM has.
Yeah.
Okay, is this part clear to everyone? Any questions on how the information is flowing, how we use these delay switch delays, and essentially how to derive each, like what is the data at each stage? So a very good exercise when you're actually working out these problems is to develop a chart which is like this. At every single point in your architecture, what is the delay, or what is the value which you expect at every time step. So that is a good reference for you to start with to build the rest of your circuit, and then it makes designing your control circuit a lot easier.
What will be the control bit for the second mux, second delay switch delay, the one delay switch delay?
So
That would contain 2 bits.
yes.
That's not 1 bit, that's 2 bits.
Right. So in this case, so essentially it would be something like the data will be like here x0, x1, x4, x5, and we would want to bring x0 with x1, x4 with like x0 and x1 in the top and bottom, x4 and x5 in the top and bottom. So in that case, we would essentially have a control signal which would be toggling every alternate bit.
Okay, yes.
So generally for these,
The LSB.
yes, the LSB. And depending if you have pipeline stages or not, whether we take LSB directly or we take inverted LSB.
Yeah.
So yeah, generally speaking, for these MDC circuits, when you have a D delay switch delay, the sequence is usually like it repeats after every D cycle. So in this case, if it's 2 delay switch delay, here we have 2 zeros, 2 ones, 2 zeros, 2 ones. But this is not for all cases, you need to work it out, but for a lot of cases, this is the general format which it follows. So yeah, any questions about the implementation thus far? And next slide I'll go over like how do you actually, like a quick slide on how do you verify this design. Okay, if no questions, I'll go to the next slide, which is, so verification, what you essentially need to do is you can think of it as 2 steps. The first step is a very simple verification just to make sure that you know that your circuit works or not. Something very quick, very easy to implement, so you can catch out all the bugs very quickly. And then you can think of as a more elaborate verification where you handle like more complicated cases. So to initially test your design, a very simple test would be just passing all ones to your inputs, or passing a simple sine wave, like for example, sine of 2 pi kn. In both cases, you'd want the result such that only one single bin of the FFT has any value and everything else is 0 in both these cases. In the first case, it'll just be the 0th bin. In the second case, it'll be the kth bin of the FFT. So the reason why I'm bringing this up is usually these tests are very easy to implement. All ones is just connecting the input to one in your test bench, but they can eliminate almost 90% of your bugs, right? Because the, let's say, the beauty or the complexity of the FFT is that if you have a mistake, it kind of propagates throughout your entire design. For a more thorough test, like when you actually, let's say, finish your design, you verified a simple functionality, everything looks fine, what would be a more thorough test? A more thorough test would be like something like a mixture of sinusoids. Say, for example, you mix, let's say, 3 or 4 sine and cosine waves of different frequencies. So what you can do is you can create something like a MATLAB script to essentially take these values and then generate the output. And you would essentially, in that MATLAB script, you would convert that to like a hexadecimal value, which you then pass as an input to your test bench. So all your test bench would do is that you've seen codes before where you just read a file and line by line and just pass that input to the test bench into the design one input at a time. Similarly, when you get the output of your FFT block, just take the output and then directly store it into a file and then post process it in like an easier software like MATLAB or Python. So that way you don't need to implement things like reordering circuit, you can handle all of those things within your MATLAB or Python script. So this way you can get a more like versatile way to check it, and then you can also compare the results you get of your block versus like a standard implementation in MATLAB or Python. So is the verification part clear to everyone? Any questions? Okay. If no questions, that's all I had for today.
Excellent. Okay, very good.
Thank you.
I think this was excellent.
Yeah.
Well,
I'll send the slides over to Professor to upload in Canvas. Also, at the end of the slides, I've just collected questions which students have asked me over the years, and with answers. So hopefully, if you have your own questions, if you look at the end of the slide, you should see a bunch of answers which may or may not help you in those questions. Right. Thank you.
thank you, Nanda. It was a good presentation. I think that those of you who want to do that thought process and developing that architecture would be very, very good. Okay, so is it your mouse? Okay, so I would like as many of you to do these FFT Verilog projects, because that's really in a way, I mean, all the things you have been learning for many, many weeks, you are now putting all of that to a nice implementation. So we can discuss more about that. I think some of you may be interested in real FFT, some may be interested in complex FFT. So let me just mention a couple of things. By the way, I've made all the sample exams visible to you. So don't worry about the first two links. We don't need to review that, but in a way, review these problems from 2017, 2021 midterm. I think there was an unfolding problem, and midterm 2 from last year, 2019, 2015, and that's when Nanda took this class, and only review the first couple of problems, 2014, and there is also something else here. So all of these are visible, so please review during the weekend. Some of you have been turning in homework late, but I suggest you turn in homework. If you are turning in late, please do so by 3 p.m. tomorrow. You can push your homework inside my office, 6181. If you need extra time, if I place the solution, then I will not grade your homework. And I do want to grade your homework at least by, let's say, Saturday noon or early afternoon, so I can post the solutions and you have a chance to review what was wrong and what you did. So, okay. Yeah, there are a lot of problems on folding, systolic arrays, some theoretical trying to prove why some folding sets are not feasible. Read those kinds of things. Okay, here is what I was looking for. I was trying to find out these handouts. Okay, so we spent some time talking about the two parallel FFT architecture. There is more in the paper, particularly 4 parallel and radix 2 squared and radix 2 cube. So let's take a quick look at couple other papers. In many applications, the signal is real. So if you are looking at what the pacemaker does by taking the electrodes from the heart, or you are thinking about a neuromodulation device for deep brain stimulation, and those are collecting signals from the brain. Those are all real signals. So how can we, intuitively, as you saw from Nanda's clear presentation, one complex butterfly is really two real butterflies. And so in a way, if the signal is real, I should be able to reduce the number of butterflies by a factor of 2 intuitively. And that wasn't really shown anywhere until my visitor, Mario Garrido, he came to do his PhD thesis research here. He was taking this class in fall 2007. And when he came here from Spain, where he's on the faculty now in Polytechnic in Madrid, so I tasked him with working on the real FFT, and that's the paper. So he did some very interesting work, and I think the idea is trivial as always after the fact. But so let me just briefly explain to you what is the optimization process of the real FFT. Okay, so in this diagram, we are looking at, okay, so that's the 16-point real FFT. So the signals marked 0 through 15 on the left side are real signals, and the real FFT satisfies conjugate symmetry. What does conjugate symmetry mean? That means xk is the conjugate of xn minus k. So for example, on the right side, when we are computing the DFT coefficients, for example, this coefficient number 9 will be the conjugate of 16 minus 9, which is 7. So x9 will be conjugate of x7. x1 will be conjugate of x15. And x4 will be conjugate of x12. So in a way, if you recall what is this coefficient x0, coefficient x0 is just the sum all of the inputs. So that's a real quantity. Similarly, x8 is 0 minus 1 plus 2 minus 3 etc. So that's also a real quantity. So 0 and 8 are real coefficients. That means their imaginary value is 0. And 4 is conjugate of 12. 2 and 10 are conjugates of 16 minus 2, 14 and 16 minus 10, 6. And 1, 9, 5 and 13 are conjugates of 15, 16 minus 9, 7, 16 minus 5, 11, 16 minus 13, 3. So I think the most interesting part of what Mario did was quickly to recognize a pattern that these boxes that you are seeing that are dashed here are redundant coefficients which we can throw out. So I don't need to compute anything. So for example, this x12 we don't need to compute that. So that means that butterfly that was computing 4 and 12, I can now use a half complex butterfly. So that one complex butterfly can be replaced by a half complex butterfly, which would be the equivalent of a real butterfly. Now, if you look at computing 210, that's one complex butterfly, and 6 and 14, that's another complex butterfly. So out of those two complex butterflies, I can throw out one. So that dashed line could be thrown out. Similarly, 1, 9, 5 and 13 are computed by two butterflies, two complex butterflies, but I can throw out the two complex butterflies at the very bottom that are redundant in the computation. The signal is real. Now we just don't throw out those dashed lines in the last column, but we backtrack and see how far I can go to the left. So for example, in this x12, I just throw out half a butterfly at the very end. But if you look at 6 and 14, that whole butterfly, so that's thrown out, and you then backtrack, and these two I don't know if you can see, are you able to see my mouse movement? I can't see from here, but yeah. Okay, so you backtrack, and then this circle here and this circle here, that's really computing another half a complex butterfly. This is computing another half a complex butterfly. So this stays right here that used to be, so how many butterflies here? 1. So let's take a look at this something marked 04. So 04 I threw out half the butterfly. I don't need to compute that bottom. 2 and 6 I threw out that butterfly. So this used to be 2 butterflies. Now we are throwing out 2 half butterflies. That means we are left with 1 complex butterfly, which really means that would be equivalent of 2 real butterflies. So you can see how the so-called 2 complex butterflies now become 2 real butterflies. That's what happens. The data path in a way eliminates half the computations. So this last part here, the 2 complex butterflies, backtrack to stage 3, we can throw all of that out, backtrack to stage 2, and if you backtrack to stage 2, we see that 4 half butterflies can be thrown out, 4 half butterflies. That means this whole thing, which had 4 complex butterflies, now becomes 4 real butterflies. By the way, the stage 1 is all real. All the signals are real, all the butterfly outputs are real. So there is nothing to throw out here, there is no imaginary part. And if you throw out the dashed parts and express the complex, half complex or other complex butterflies, then those would become real butterflies. So, for example, this butterfly here can be divided into two real butterflies. I keep one here, I keep one right here where I threw out the quantity. So, the two complex butterflies become four real butterflies. I keep the two real butterflies here, and the two butterflies are placed where the two were thrown out. So, what that means, very interestingly, after I remove the redundant things, expand the complex to real, I have a data flow graph that looks very much like the one we have right now in the complex case. And then you can apply the folding the way we have talked about in the class to design an optimized architecture that is now going to use the least amount of area, consume the least amount of power to compute the real FFT. So, this is the diagram in figure 2 is after we have thrown out the dashed parts, and the diagram in figure 3 is after I have expressed everything in terms of real butterflies. So, for example, in stage 2 bottom, by the way, stage 2 top part is all real. Why? Because there wasn't any twiddle to multiply. These were all w to power 0. Okay, there is little more going on. There is some twiddle shifting that I haven't talked about, but at the ultimately, okay, I mean I think these things used to be w to power 0, 1, 2, 3, 4, 5, 6, 7. Some twiddles are pushed to the right. Then these w to power 0 is all 1, w to power 4 is minus j. That means you swap real and imaginary. There is no real multiplication going on, and once you swap them, expand these half complex butterflies, they become real butterflies. So, I fill that up, and at the end, after you fill all these up in the real butterflies, the diagram looks exactly like what we had, and some of them just are there is no real butterfly computation. These are just simple connections, but that's really the optimization to design systolic type. I mean systolic type, or you can say radix 2 or radix 4 delay commutator type circuits. So, we won't go into a lot of detail unless some of you might be interested in implementing the real FFT. By the way, I think the real FFT and students in this class have implemented all kinds of FFTs in the past. Yeah, so they've implemented different lengths, real complex, different radix. I didn't talk about radix 2 squared, but it's probably not necessary to talk about that right now. So, if we look at I can just walk through quickly a couple of other papers. So, this was again Salehi's paper. Salehi came from Iran to do his PhD thesis research, and ultimately at my suggestion, not that what he planned, but at my suggestion he didn't want to go back to Iran. So, I suggested, okay, now instead of you drop out of PhD program in Iran, you apply to be PhD student here, and which he did, and he became brand new PhD student and finished his PhD thesis on DNA computing. But the work that he did for his supposed PhD thesis in Iran that never really happened is also interesting. He took that paper by Mario and did some more generalizations. So, the xk, as I was saying, the conjugate property. So, this paper shows a little more detail So that's the diagram. The Garrido paper doesn't show all the details very clearly. So for example, let me see here. This diagram shows the clock cycles, just like what we have gone through in the complex case. It shows when there are available clock cycles 5, 7, and this butterfly is executed at 7. But also it shows the control bits, the control bit patterns, M zeros followed by M ones for that M delay, switch delay. That's what Nanda was explaining to you. But the control signal here changes a little bit. So there are two different switches, so-called switch 1 shown here, the control bits M zeros followed by M ones, so-called switch 2, two M zeros, let's see here, two M zeros, yeah, there is some different pattern here, and so those are the control bits. So let's take a look at this design here. So butterfly 4 delay switch delay, butterfly 2 delay factor multiplication, 2 delay switch delay, butterfly 2 delay switch delay. This is a canonic sign digit multiplication. Nanda didn't talk about canonic sign digit. So when we already know when the angles are pi by 2, that 2 delay factor is j. When the angle is pi, that's minus 1, and when the angle is minus pi by 2 or 3 pi by 2, that's minus j. So what we didn't talk about, when the angle is pi by 8, e to the power j pi by 8, e to the power j 5 pi by 8, e to the power 4 plus e to the let's say pi by 8, 45 degrees, 135 degrees, and then 225 degrees and 315 degrees. Then those coefficients are going to be 1 by square root of 2 plus or minus j 1 by square root of 2, and that 1 by square root of 2, which is 0.707, could be approximated by few non-zero bits, so-called canonic sign digit, and that's why those multipliers could be implemented by so-called canonic sign digit multiplier. Yeah, I didn't talk about a lot about arithmetic, which, as I suggested, you can watch from the YouTube, and we talk about canonic sign digit representations. Okay, so what is more interesting in so this is figure 7, 4 parallel 16 point when the signal is real. But what is more interesting is sometimes I may want to compute the inverse FFT, right? So what happens, as the title suggests, so we can exploit that symmetry to simplify the data flow graph or the dependence graph when the signal is real, but we can also simplify the data path or the dependence graph or the data flow graph when we are computing the inverse FFT of a conjugate symmetric sequence. So if you start with a real signal, take the FFT, that's conjugate symmetric or Hermitian symmetric, if you want to think about it, and then you take the IFFT of the conjugate symmetric sequence, then the output is real. And so that's that same idea that wasn't in the Garrido paper is, so Salehi worked that out. And if you look at the, so that's 32 point. Okay, so let's look at this figure 12. So if you look at figure 12, so this x12 is conjugate of x4. And so in other words, this x0 to x15 is a conjugate symmetric sequence, and that means when I'm computing the IFFT, by the way, you probably remember the inverse FFT is very similar to the FFT. All you have to do is take the conjugate of the Tweedle factors. So you have to take the conjugate of the Tweedle factors. So then I can, instead of removing redundant parts at the end and backtracking, I can remove computations in the beginning and go all the way forward as far as I can, so that I don't compute redundant parts. So the same idea could be used to compute RIFFT as well for the two parallel case. And the last paper that I want to briefly talk about, which is so we have spent a lot of time talking about two parallel, and I didn't talk about a lot, but you can design 4 parallel. But suppose that you have a signal channel and you don't want to process in 2 parallel, and then this paper shows how to do serial real FFT. So again, intuitively, if I don't want to do 2 parallel and the hardware utilization is 100%, then in a way I should still be able to reduce the number of butterflies by another factor of 2. So I started with a complex butterfly in the complex case, then that became a real butterfly in the real FFT case, in 2 parallel case. And if I want to process one sample at a time in this so-called serial real FFT, then each butterfly stage now should have half a butterfly, not even one whole, should have half a butterfly. And the control signals are all quite complex, more complex than what Nanda described for the, by the way, this was Nanda's course project in fall 2015 when he took this class. That was his project. He spent an enormous amount of time, did an outstanding job, and I picked him up to the research group after the class. So there is a lot of so there are a lot more permutation circuits, and you can see these control bits, control signals being generated, and he spent a lot of time. And so what I want to show you, by the way, maybe we are better off looking at the PDF. I can't see at least clearly in my computer screen. So the diagrams, yeah, so you have seen permutation circuits like that. You have also seen the permutation like figure 3 that allows us. So if you look at what figure 3 shows, I can go all the way forward. That would be L1 samples. When I take the output from L2, push it back, then I can have L2 plus L2 plus L1 minus L2, and that would be L1 plus L2. So I can generate L1, I can generate L2, and what happens if I take the output from L1 minus L2, feed it at the end here. So that goes through L1 minus L2 plus L2, that's L1, and then that becomes 2L1 minus L2. So you can take the input to the output, so that's 0. So I can get all these combinations. And we have seen there is the reason why I was spending time to show you our friends, because that's what we need. Those permuters and the delay switch delay are the basic building blocks of computing FFT in hardware. Okay, that's the final diagram, figure 4. 16 points, so we take one single input shown at the input left side, and these are half butterflies. So what you see, well, I guess these are written quarter. So when you see this quarter, that's really a quarter complex butterfly, which is equivalent of half a butterfly, half a real butterfly. and then these permuting circuits, permutation with 1 and then 2, there is that permutation 6 and 1. Okay, so yeah, so it's far more complex, and this diagram shows the control bits S1. There are several control bits. So this diagram has S3, S4, S5, S6. The diagrams in figure 5 have S1 and S2. So there are 6 control bits needed for that one. There is a timing diagram like the one I have shown you before, which clock cycle what butterfly is executed, that helps you understand what's going on. So that's the serial real FFT, and that's the reordering circuit. Okay, so that's kind of a brief review of the FFT. I'll stop here. The sample exams are on the website, Canvas site. You can read them. Okay, so anyway, see you next week. By the way, I should say that the exam will be 9 to 11 on Thursday. If you think you will get more points, some of you, you can always talk to me. I am glad you pointed out the mistakes, Brandon. That was good. Otherwise, I wouldn't notice. You can turn in your homework